Okay, all right. Welcome once again. Today we are going to be looking at electrolysis. So we're going to be looking at electrolysis today. My name is Remain Anjan Excel, and I'll be your teacher for this particular topic on electrolysis. Without much ado, let's look at the learning objectives for this topic. It is expected that by the end of this lesson that you should be able to, one, distinguish between electrolyte and non-electrolyte, perform calculation based on Faraday's law, identify suitable electrodes for electrolytes, and specify reactions at the electrodes, and also to be able to determine products at electrodes, identify factors affecting products of electrolysis, state applications of electrolysis, identify electrochemical cells, and calculate electrode potentials, and finally describe corrosion prevention methods. So these are the learning objectives for this particular topic. So we move on to the body of the lesson, and we consider an introduction to electrolysis, where we attempt to define what electrolysis is. And in attempting to define electrolysis, we'll say that electrolysis is the chemical decomposition of a substance by passing an electric current through it. The chemical decomposition, that's the keyword there, chemical decomposition of a substance by passing an electric current through it. And that is what electrolysis is. Okay. All right. Having said that, let's push it a bit further. What are the requirements for electrolysis to take place? One, we need an electrolyte. An electrolyte is basically an ionic compound in molten or aqueous state. So for us to carry out electrolysis, we need an electrolyte. Apart from an electrolyte, we equally need electrodes, and most of the time they come in two. You have the positive one and then the negative one. We are going to look at it. We'll talk about it as we move on in the course of the lesson. So we also need we need electrodes. Electrodes are basically conductors like graphite or platinum, and so on and so forth. So we also need external power source. An external power source is needed. Either a battery or a DC supply will be fine. Um, so this is basically how the electrolysis setup is. You have the electrode, like I said before, there are two. We have the cathode, then we have the anode. The cathode is negatively charged. The anode is positively charged. Then you have the electrolytes, which is the ionic compound that is in molten or aqueous state, and then we have the external power source. So this is how basically an electrolysis setup looks like. You understand? Okay, all right, let's move now. So electrolyte versus non-electrolyte. In looking at this, we'll just do a little table, Electrolytes, in terms of conducting electricity, electrolytes conduct electricity, while non-electrolytes do not conduct electricity. Example of electrolytes include sodium chloride aqueous, H2SO4 aqueous, and so on and so forth. Non-electrolyte, on the other hand, example includes sugar, ethanol, and so on. So we also have in terms of ionization, electrolytes will produce ions, and then non-electrolytes, they do not produce any ion whatsoever. So we can have a setup whereby we have an electrolyte, bringing up, lightning of a bulb, so to speak, just like we have in this setup. When you have a non-electrolyte, you discover that no current will pass through to light up the bulb. When the electrolyte is weak, yes, some current will flow, but it will not be so much, so the bulb will not be radiant the way it's supposed to. Then when you have stronger electrolytes, you can see an extensive current flow, and then you see the bulb lights up brightly. So that's basically the difference between electrolytes and non-electrolytes. Okay. So we'll look at the law of electrolysis now. The first law is this. It said the mass M of a substance deposited or liberated is proportional to the quantity of electricity Q that is passed. That's the first law. The mass M of a substance deposited or liberated is proportional to the quantity of electricity Q that is passed. Okay. In terms of the formula from this particular law, we can have our M equals to Q multiplied by Mn times Fm, which equals to Q multiplied by M divided by N multiplied by F. Now, what does these letters symbolize? Let's look at them. Before we look at them, don't forget that our Q also equals to the current times the time. That's IT. So if you don't have your Q, but you are supplied your current and the time, you can easily, calculate what your charge. Oh. Pardon me, please. You can calculate what your quantity of electricity will be. Okay. All right. So our hem is the molar mass. That's capital Hem is the molar mass. Then our N is the number of electrons. Our F is the Faraday constant, which is 96,500 coulombs per mole. And then, okay, so that's that for that. So we have defined that the number M is our mass. Okay. So that's that. So the second law of electrolysis, the second law of electrolysis states that when the same quantity of electricity is passed through different electrolytes, the mass of substances liberated are proportional to their chemical equivalent. So when the same quantity of electricity is passed through different electrolytes, the masses of substance liberated are proportional to their chemical equivalent. So that's the second law of electrolysis right there. Okay, let's look at some sample questions to test out some of these formulas that we have gotten. Okay, this question says that a current of 5 amperes is passed through copper sulfate solution for 30 minutes. Find the mass of copper deposited. Find the mass of copper that is deposited. Now, looking at it, I told us earlier that if I don't have Q, but I can always calculate my Q by multiplying my current and my time. In this question, we're given a current, we're also given a time. So what we do basically is to convert that time to seconds. We convert it to seconds. And how do I do it? 30 minutes to seconds. Just multiply 30 by 60 and that will give us 1,800 seconds. So I can use that and then multiply against current and then have a now 9,000 coulombs. 9,000 coulombs. Okay. If that is the case, the molar mass of copper is always given to be 63.5 gram per mole. And don't forget that Cu2 plus require 2 moles of electrons, because it carries 2 plus charge. Okay. So therefore, our mass will be equals to 9,000 times 63 0.52 multiplied by 96,000 500. So our mass will be equal to 2.96 grams. 2.96 gram. How did we arrive for at this? Just going by this particular equation that we have here, that particular formula that we had here. So we just use that, and then that's how we arrived at 2.96 grams. So please, let's kindly take note of this and um, try to understand it so that if you see questions like this, you know how to easily apply it accordingly. Okay, so suitable electrodes down. Um, we have inert electrodes that do not react. Examples are platinum electrode and graphite electrode. Then we have active electrodes. They participate in reactions, e.g., copper anode in copper sulfate electrolysis. So they tend to participate in the reaction. Those are the active electrodes. Then we also need to talk about the choice of which electrode to pick or to choose, as the case may be. So this choice depends on one, the nature of the electrolyte to tell us which type of electrode should we should pick. If it is an electrolyte that you know that can be pretty reactive with certain, substance, you must also carefully select the electrode to ensure that okay, it is one that will not, interfere whatsoever with the process. So the nature of the electrode helps in making this choice, is a major determinant to the choice of electrodes that will be selected. Secondly, the desired products. When you have a desired product, you must also be mindful of the electrodes that you are making use. If you want a product whereby you don't want any interference or whatsoever reaction, then you'll be considering an inert electrode. So we also, or maybe you are looking at a product that you want a specific substance to come out of either the cathode or the anode. So we target or we choose a particular electrode that we know that its interference will favor the deposition of that targeted substance at either the cathode or the anode, as the case may be. Okay, so the desired product is another factor that comes to bear now. So let's be mindful of that. Very, very important that we're mindful of that. So we said that the active versus inert electrode, the actual electrode material, electron conductor may or may not be the actual species going through the oxidation for anode or reduction for cathode half cell reaction. So active electrodes, electrode material is also the substance that goes through the electrode reaction. Zinc anode will give us zinc 2 plus and that, and then copper cathode, and something like that. So the species that goes through now, what are the reaction at the anode and then the cathode? So at the cathode, what we see basically is a reduction that sees a gain of electrons or gain of electrons. So we discovered that the cathode is negatively charged. So reduction or gain of electron is what takes place at this particular, electrode. Okay. The second one is the anode, which is the positive electrode. And what happens here is oxidation, which is the loss of electrons. So we have a loss of electrons, at the anode, and an oxidation reaction or process will always take place at the anode. Okay. Now, example, electrolysis of molten NaCl. Now, this is what happens at the cathode. We see Na plus an electron giving us sodium, elemental sodium that is deposited at the cathode, whereas at the anode we have the chloride ion, you know, giving us and then the chlorine that is deposited at the anode. So basically that is what happens. So if you look at it critically, at the cathode you have a sodium that is +1, then moving to 0. That is a reduction, and that's what happens at the cathode. Whereas at the anode you have chlorine -2, then moving up to 0. That's an increment in oxidation number, and that is an oxidation that takes place at the anode. So we must be mindful of that and be able to understand that we see at the electrodes. So I'll just look at this table. It has electrolytes, cathode products, and anode products. When you have a molten sodium chloride, what you have deposited at your cathode is sodium metal, whereas at the anode you have chlorine gas. When you work with your doing electrolysis and the electrolyte is copper sulfate, what you have deposited at the cathode is copper metal, and then oxygen is deposited, is given off at the anode. Okay. Then when you have dilute H2SO4, what you have, at the cathode is hydrogen gas, and then at the anode oxygen gas. So all this, I must say, depends on the electrochemical series. The chemical series is a series, showing different metals, and the displacement of this metal, the ability of this metal to displace, or the ability of this element to displace themselves in the electrochemical series has to do with their positioning, or their hierarchy in the electrochemical series. So it is mainly dependent on the electrochemical series. Okay. So this is just like a diagrammatic outlook to what we talked about, especially for sodium chloride. You can see, diagrammatically, how it plays out, so to speak. Okay. All right. So I'll move on now, and then we move to looking at factors that are affecting the products that will be deposited type of electrolytes, is it molten or aqueous? So the type of electrolyte is a factor that affects the products, Secondly, concentration of the ions. The concentration is another major factor that affects the product that is deposited at the electrode. Okay. So we also have position in the electrochemical series. I've talked about this, the hierarchical arrangement of elements in the electrochemical series and their position in the electrochemical series tends to determine whether they can displace another element or they are unable to, so to speak. So when you have two metals or maybe two elements in solution, and you want one to be deposited at either the cathode or the anode, as case may be, one of the things that you discover is that because of the position, if you have, let's take, for instance, this is just an hypothetical example. It is not like it is how it is on the electrochemical series. Let's take, for instance, you have maybe sodium and zinc, and you want a situation whereby probably maybe your zinc is deposited on the electrode. Now, the ability of zinc to be able to displace sodium will be solely dependent on how it is positioned on the electrochemical series. If you have your zinc above sodium in the electrochemical series, so most definitely it can actually displace sodium, But if the reverse is the case, then it becomes near impossible for you to be able to displace, sodium. So position in the electrochemical series also affects the product that we get either the anode or the cathode. Okay. Another thing again that is another determinant is the nature of the electrodes. The nature of the electrodes, some electrodes are inert, some electrodes are not inert but active. So the nature of the electrode will determine the product also. If it's an electrode um, that has an impact or influence on the electrolysis, then it may sway or shift what is being produced based on certain affinity that that product has to for the electrode. So this is also another factor affecting the product. Current density and voltage is another major factor too. The current density and the voltage that is running through the electrolyte or the electrolytic cell will determine, the depositions or the product that will be formed at either of the electrodes, either the cathode or the anode. So the current density and the voltage, the current density is a little, you discover that it does not facilitate or it affects or impacts the product one way or the other. And if the current density and voltage is, of the right amount, or adequate, you also see it being you only see it impacting the product that will be deposited either the cathode or the electrode. Okay. So the next thing that we need to look at, I haven't talked about the factors affected products, is to look at the application of electrolysis itself. Electrolysis is applied in extraction of metals, e.g. sodium from sodium chloride, so we can use it for extraction of metals. We can also use we can also apply electrolysis in manufacture of fluorine and sodium hydroxide, and these are important, chemicals. So manufacture of fluorine and sodium hydroxide is one application of electrolysis. Another application is in the purification of metals. So metals like copper purification, can be carried out using electrolysis. So we can apply electrolysis for purification of metals. Okay, we can also apply electrolysis in the just a minute. We can also apply electrolysis in electroplating. Electroplating is simply coating an object with metals, either to protect it from rust or corrosion, as the case may be. So coating objects with metals like electroplating is another application of electrolysis. Another application of electrolysis. Okay, so the electrochemical cell is the next one that we need to look at briefly. Devices that convert chemical energy into electrical energy or vice versa are referred to as electrochemical cells. They convert chemical energy into electrical energy or vice versa. Okay, so that's electrochemical cell. There are different types of electrochemical cell. Number one is the electrolytic cell that needs external voltage, external source of power. Okay, so we have the electrolytic cell. The second type of electrochemical cell is the galvanic or the voltaic cell, which generates electricity spontaneously. So that's the second type of um electrochemical cell. So an example is the Daniel cell. The Daniel cell is an example. So we have something like this. So this is the electrolytic cell. You can see the setup. You have the two electrodes. You have a battery, or a power source, and then for the galvanic cell, you can see that you always have a salt bridge. So replacing the battery, we will have a salt bridge that connects the two, cells together. So we have the anode in one, then we have the electrode in one, then we have the salt bridge that is hovering over them like in the middle. And you can see that. So those are the types of the electrochemical cells that we have. Okay. So we now go to electrode potential and half cell reaction. Electrode potential and half cell reaction. So we said each half cell has an electrode potential. Each half cell has an electrode potential. Okay. Um, we must also know that standard electrode potential measured against hydrogen electrode, that is 0.00 voltage. So the started electrode potential is often measured against the hydrogen electrode, which is like a standard, which is 0.00 volts. Okay. Cell potential, can be calculated using E cell. That's the electrochemical this thing of the cell equals to E cathode minus E anode. E cell equals to E cathode minus E anode. So we subtract what we have, the cathode from the anode. So whereas E cell represents the overall cell potential, E cell represents the overall cell potential, also known as the electromotive force. It's also known as the electromotive force, which is EMF. So E cathode represents the reduction potential of the electrode where reduction occurs. So that's how the cell potential is calculated. E cathode minus E anode. Okay. So the E anode represents the reduction potential of the anode where oxidation occurs. Okay. Okay. So we must note that positive standard cell potential equals to reduced at the cathode. So there will be a reduction at the cathode. Okay. So let's take note of that. Let's look at an example to bring that topic, sorry, the formula to utilize the formula. Okay. So when you have zinc 2 plus moving to give us zinc, and equals to minus 0.76 volt, and then your copper 2 going to give copper, and that's plus 0.34 volts. Okay. Okay, so it said we should find the cell potential. Find the cell potential. We remember that E cell will be equals to E, I think E cathode minus E anode. Okay, am I correct? Let's just confirm that quickly. Yes, I'm correct. E cathode minus E anode. So I just want to be sure. So that's what that is. So when you do that, you end up having a cell potential of about 1.10 volts. Positive value equals to spontaneous cell, and that's the implication. Okay, corrosion and prevention is another aspect that we need to look at. Corrosion and prevention. Corrosion gradually Corrosion is the gradual destruction of metals by environments, e.g. rusting. The gradual destruction of metals by environment, e.g. rusting, is what we call corrosion, okay? Methods of prevention of corrosion. The following are the methods. We can do what we call the cathodic protection. We can also do what we call painting. It protects or prevent corrosion. Or yes, so cathodic protection, painting, greasing or oiling, electroplating, then iron protected by attaching sacrificial anode, e.g., when you add zinc to it, so to speak. So these are the methods to prevent corrosion. Cathodic protection, painting, greasing or oiling, electroplating. Okay, all right now. So we move to the next step, which is the end of the lesson evaluation. But don't forget that in the course of this lesson, we have been able to look at what electrolysis is. We have been able to touch on electrochemical cells. We have differentiated between electrolyte and the non-electrolyte. And then we have looked at simple calculations that involves, cell potential and so on and so forth like that. So let's take note of that. So the next thing is to evaluate this lesson. But please, if you have a question on this topic, please kindly put it in the comment section. If you have an area that you desire that I should clarify on, please put it in the comment section so that I can react appropriately to it. What is produced at the cathode during the electrolysis of water? What is produced at the cathode during the electrolysis of water? Is it oxygen? Is it hydrogen? Is it chlorine? Is it sodium? Hmm. So, what is produced at the cathode during electrolysis? Please let me know what your answer is in the comment section, and then I will comment and or react to it appropriately. The second question says that which of the following is not a component of an electrolytic cell? Which of the following is not a component of an electrolytic cell? A, electrodes. Which of the following is not a component of an electrolytic cell? A, electrode, B, electrolyte, C, battery, and then D, beaker. So the only one that is not a component there is what? Now, please tell me in the comment section, and then I will react appropriately. The law stating that the mass of substance liberated is proportional to the quantity of electricity passed is called Avogadro's law, Faraday's first law, Boyle's law, Dalton's law, and so on and so forth. So please, let's go through them and put your answer in the comment section. So please do more practice questions on your own, so that some of those formula that we have treated can easily, stick and you can easily recall them. Okay. All right. Thank you so very much for watching and for listening. I hope you've gotten something in the course of the teaching. So please don't hesitate to walk up to So that's that. So we can just put your questions or anything that you're not clear about in the comment section. So I'll see you in the next video. Thank you.